In this video, we're going to talk about the interior and exterior angle theorems in triangles. So the first theorem, you guys already know, it's the sum of all the angles in a triangle is 180 degrees. So what you need to know now in geometry is how to prove this theorem. So the first thing I want is just to show you kind of a visual of why the angles have to be 180 degrees. So if we look at this diagram here, here's my three angles. To show that those have to be 180 degrees, if we basically translate or rotate these two base angles here, the green and the blue angles, and we piece them together with the pink angle, you can see that all three of these angles now form a straight line, which means they have to be 180 degrees. So the sum of the interior angles have to add up to 180. If you actually cut apart any triangle and piece together the three angles, they'll always form a straight line, so 180 degrees. So the proof of that is going to be a little bit different, but it's going to be kind of the same idea. We basically are going to show that these angles up here can be pieced together with angle 2 and form a straight line, which will show that they all have to equal 180 degrees. So let's start with our two columns here. So we're going to have our statements and reasons. And since this is a theorem, this is one of those proofs that's going to be a little bit trickier, but it's the proof that will always work. So it's not something new each time you prove it. So the first thing we're going to do is we're starting with our triangle. So our given is going to be, okay, we're starting with triangle ABC. And then our second thing that we're going to have to do, so I'll just write given, is we're going to have to construct what's called an auxiliary line, which is basically a line that's going to be parallel to line AC. So I'm just going to say draw a line parallel to AC passing through point B. So the reason for this is because there can only be one parallel line to line AC that passes through point B. There's only one possible line that you can draw. So there is only one unique line parallel to AC passing through point B. So this is that step that we've seen with other theorem proofs that's kind of like the unique step that you have to actually like create something. So that really only happens whenever you're trying to prove theorems. So let me go ahead and sketch this. So I'm going to draw a line that's parallel to line AC that passes through point B, and I can do this because there only exists one of these. There's only one line that could be parallel to a given line passing through a given point. So this line is parallel to line AC. So now that I have a parallel line, now I can say that I have some congruent alternate interior angles or corresponding angles. Look for those types of angles. So if you look, angle 1, and if I call this angle 4, those are now going to be congruent because those are the Z-shaped angles, the alternate interior angles. And I can also say angle 3 and let's call this angle 5 are going to be congruent because, again, that Z shape, the alternate interior angles. So I can go ahead and mention that next. So I have angle 1 is congruent to angle 4, and angle 3 is congruent to angle 5 because parallel lines imply congruent alternate interior angles. Make sure that you say that because the lines are parallel, that's why they're congruent. And then the next thing is I can say, well, if you look, angle 4, 2, and 5 all have to add up to 180 degrees because they form a straight line. So I can say the next step here, the measure of angle 4 plus the measure of angle 2 plus the measure of angle 5 is equal to 180. And that's because angles that form a straight line add to 180. So then from there, instead of having angle 4 plus angle 2 plus angle 5, we know that angle 1 is equal to angle 4, so this is really like angle 1. And I know that 3 and 5 are equal, so instead of having 5 up here, angle 3 is really equal to that. Kind of like that visual you just saw where we took these two angles and we brought them up. That's exactly what we're doing here. So I'm going to replace, instead of angle 4, I'm going to replace it with what it equals. So it equals angle 1. I'm going to keep angle 2 the same. And then instead of angle 5 here, I'm going to replace it with what it equals, which is angle 3. So now I've just stated that angle 1 plus angle 2 plus angle 3 is 180 degrees. So the sum of the interior angles is 180 degrees. My reason for that is substitution. I just substituted in parts that are equal. And that's it. So that would be the same proof anytime. So like I said, the unique part is that number 2. Once you get number 2, well then it's more straightforward from there. For the next theorem here, that's called the exterior angle theorem. So you should have learned this already in middle school. But just to refresh your memory, the exterior angle, well, first of all, an exterior angle is any angle outside of the triangle. So this angle right here is your exterior angle. So that means that this angle, according to this theorem, is equal to the sum of the two non-adjacent interior angles. So this would be the adjacent interior angle because they're next to each other. So this exterior angle would be equal to the sum of these other two angles. So basically, if you look here, angle A plus angle B would be equal to angle ACD. So meaning if I put numbers in here, angle 1 plus angle 2 is equal to angle 3. So I'm going to also add that. So that's what the theorem's saying. So let me show you why that's true, and then we're going to look at a proof for it. So if I look at this picture, here's my two non-adjacent interior angles. If you actually do some transformations, in this case it's translation, rotation, then a translation, you see that those angles that were up here completely take up the exterior angle, meaning they're equal, the sum of those two are going to be equal to the outside angle. Essentially, the reason for that is because these three interior angles have to add up to 180, and this exterior angle and this have to add up to 180. But since these two pieces equal these two pieces, and you have this common angle, if you take that away, you're going to end up with the sum of these having to equal the exterior angle. So let's look at that a little bit more, because I know that kind of explanation wasn't the best. So let's look at the proof for it. So here's my situation where I want to prove that the measure of angle ACD is equal to the sum of the two interior angles. I'm actually going to switch that. Let's just put 1, 2, and 3 in there. That'll just make it easier. So this is saying the measure of angle 3 is equal to the measure of angle 1 plus the measure of angle 2. So that's what we're going to prove. So starting with our statements and our reasons. So we start with our given. So we're given triangle ABC with exterior angle ACD. And then if you remember what I said, I'm going to call this angle 4. Since we're not proving the interior angle theorem, I can use it. So these three angles inside of the triangle would have to add up to 180 because they're the angles in a triangle. So I can say the measure of angle 1 plus the measure of angle 2 plus the measure of angle 4 would have to equal 180. And that's because all interior angles in a triangle add to 180. And then I also know that these two angles are going to have to add to 180. So that means I can mention that. So I can say the measure of angle 3 plus the measure of angle 4 is 180. And that's because angles that form a straight line add to 180. And then if you look, these two things have to be equal because the three interior angles would have to equal the sum of the angle 3 and angle 4, because since they both equal 180, so since this equals 180 and so does this, well, they're essentially equal to each other by substitution. So step 4, I can say angle 1 plus angle 2 plus angle 4 is going to be equal to angle 3 plus angle 4. I just set them equal. So the reason for this is going to be substitution. You're just plugging in. I plugged in 3 plus 4 instead of 180. And then now you have a common piece here. I have angle 4 on both sides. So if I subtracted that off, I would be left with angle 1 plus angle 2 equals angle 3, which is exactly what I want. So you have that common piece used in both equations in 2 and 3. So now, before I can subtract, though, you do have to say it's equal because you have to show that you're subtracting off an equal piece. Even though, yes, angle 4 is equal to angle 4, we have to mention it. So the measure of angle 4 is going to equal the measure of angle 4 by reflexive property. It's the same angle used twice. So it's shared. So then from here, the last step is going to be, okay, so now subtract angle 4 from both pieces. So if you subtract these would cancel. So I'm not going to actually cross those out. So I would have angle 1 plus angle 2 equal to, so if you cross off angle 3, well, you cross off angle 4, you're left with angle 3. And then the reason for this is going to be the subtraction property of equality. You're starting with something that's equal and you're subtracting off the same piece from both sides. So essentially, let me use a highlighter to kind of cross it off so you can still see it, but you know I crossed them off. So those canceled and these canceled when I subtracted. So that's exactly what you needed to prove.